Hi everybody and welcome to the final video in the sound generation with neural networks series. Last time we trained a variational autoencoder with a sound digit dataset. This time we want to take that model and actually start generating sound digits. To achieve this goal, we're going to be having a plan divided into two steps. First, we're going to be building a sound generator class that's going to have all the facilities that we actually need to generate this sound digits, and then we're going to build a generate.py script that's going to be using the sound generator class to generate audio so that we can see and test how good the sound generation is. Perfect. Before we get started with the implementation, I want to give you a quick refresher on how we can generate audio with variational autoencoders and explain what we'll be doing with the sound generator class. So the stuff that I'll be talking about right now, I've already covered them quite in detail in previous videos, and actually I'm going to leave you like the video here, so where you can find way more information about all of the things that I'll be touching upon right now. But let's get started. So generation with variational autoencoder. So here you have a simplified version of our variational autoencoder with the encoder parts, the latent space, and the decoder. Now, if we want to generate audio, what we are going to be doing is passing in a spectrogram, and the spectrogram that we'll pass in comes directly from the train set. Now, once we pass in this spectrogram, what we'll get after the encoder does its job is a point in the latent space. And now we'll be using this latent space, or this point in the latent space, and fitting it into the decoder. And what we'll get outside as an output is another spectrogram, which in this case is the reconstruction of the original spectrogram. Now, we'll be focusing on this way of generating stuff, basically already using like stuff that the variational autoencoder has already seen, because of a simple reason, because we want to compare the original audio associated with this spectrogram to the one that we reconstructed with our variational autoencoder. Now, of course, there's another way of generating sound digits or any type of data with variational autoencoder, but we're not going to implement that, but you can easily do that if you want, because you have all of the facilities and all of the different methods in the variational autoencoder class. Now, for this second approach, you just drop the encoder part of the variational autoencoder, and what you do here is you just sample a random point, if you will, in the latent space, and then you fit it to the decoder, and the decoder hopefully will come up with a new spectrogram that the generator basically has never seen before. So yeah, these are like the kind of two approaches that we have here. Now, the next step is moving from spectrograms to audio, because if you followed along so far, you'll know that by now what we do is we generate spectrograms. But of course, in the end, we want some audio files. And so how do we do that? Well, we start from spectrograms, then we apply the inverse short time Fourier transform using specifically the Griffin-Lim algorithm, and we get as an output a waveform associated to the original spectrogram. So what the Griffin-Lim algorithm does, it's basically it reconstructs the phase, and it tries to create in a way that makes the most sense possible. It doesn't work always like that great, as you'll hear, but is a basic implementation that we can use in Librosa directly, so we don't need to get into the details of how to reconstruct a phase starting from a magnitude spectrogram like the one that we have in the slide here. Okay, so this is the plan. This is the high-level intuition. Let's get started with the implementation of the sound generator class. So sound generator. Okay, so let's write a simple docstring here. So sound generator is responsible for generating audios from spectrograms. Okay, this looks good. Now let's create the constructor first. Now the constructor takes two arguments. So one is the variational autoencoder and the other one is the hop length. We'll need information about the hop length in order to reconstruct or to actually pass from a spectrogram to the signal, so to the waveform. Here we'll do a self.vae and we'll pass the variational autoencoder, and this VAE is basically the variational autoencoder class or object that we have here defined in this other module. Okay, and then we have the hop length, and so we'll do a self.hop length and we'll pass the hop length there. And finally, we also need a private attribute, and this will be the min-max normalizer. Okay, so let me import the min-max normalizer. So we'll do from preprocess import min-max normalizer. Now let's jump in this. So we defined the min-max normalizer in the preprocess model, and if you want to get the details about the min-max normalizer and also about the preprocessing pipeline that we use to preprocess our audio data, just go check out this video if you haven't done so. Cool. And we need this min-max normalizer here, and we should pass the min value, which is 0, and the max value, which is 1. Okay, now the question is, why do we need this min-max normalizer in the SoundGenerator class? Well, that's because the spectrograms that we'll be generating should be ideally normalized. And so we want to denormalize them before converting them into audio signals. Okay, so now onto the main method of this class, which we'll call simply generate. So generate takes two arguments. So we'll have spectrograms, and so this is a list of arrays where each array is a spectrogram, and then we'll have another variable called min-max values. So this is a list of dictionaries, and these are the minimum and maximum values of the original spectrograms before the normalization process, of course, associated to these spectrograms here. And we'll need that once again for denormalizing the spectrograms that we'll generate. Okay, cool. So now what we want to do is actually reconstructing the spectrograms, as we just showed in the slides at the level of the intuition earlier. Okay. So for that, we'll be using a method that comes with VAE, which our variational autoencoder class that's called reconstruct. And reconstruct gives us back a couple of arguments, or a couple of variables. So one is the generated spectrograms, and the other one is the associated latent representations. Okay. So here we'll do a self.vae.reconstruct, and we'll pass the spectrograms like that. Okay, so now we have the generated spectrograms and we have the relative latent representations. We're not going to use the latent representations, but the only thing that we'll do with that is just we'll return them. Okay. But before we can return information, data from this generate method, we need to convert the generated spectrograms to audio signals. So how can we do that? Well, we should create another method that's going to be responsible for converting spectrograms into signals. And so here we'll do a signals is equal to self.convert spectrograms to audio. And here we should pass the generated spectrograms as well as the min-max values. Like that. Cool. Of course, we haven't implemented this method yet, but we'll do it in a second. And here what we get back is a list of signals. And now we're ready to return both the signals as well as the associated latent representations. That's cool. Now, on to the final step for this class, and we'll need to define convert spectrograms to audio. And here, we already know that this function accepts a couple of arguments. So one is spectrograms. I have some kind of issue typing spectrograms. Okay, so spectrograms and then min-max values. Cool. Okay, so here we need to go through each of the spectrograms and do this conversion. So as a first thing, I want to create an empty list, and I'll call it signals. And this is like where we're going to be adding each of the converted spectrograms, and then we'll return it in the end. And then what I want to do here is I want to go through all the spectrograms one by one and through the associated min and max values for the original spectrograms, right? The denormalized one. So here we'll do for spectrogram and min max value, and we'll use zip. Oops, and here we'll zip spectrograms and min-max values, like that. Cool. And so here we have a spectrogram and the relative min value and max value for the denormalized log spectrogram. Here we should do a few things. So first we should reshape the log spectrogram. Now, in reality, what we're getting here is not a spectrogram, but it's rather a log spectrogram, and we need to reshape it, and we'll see why that's the case in a moment. But let's go through all the steps one by one, and then we'll see why we should do all of these things. Okay, so now we've reshaped the log spectrogram. The next step is that of applying denormalization. So apply denormalization. Okay, then we want to pass from log spectrogram back to normal spectrogram, linear spectrogram. So we'll do log spectrogram, and we'll pass to spectrogram, linear spectrogram. And finally, we'll apply the Griffin-Lim algorithm. In other words, we'll apply the inverse short-time Fourier transform so that we'll get a signal. And once we have the signal, we'll append signal to the signals list that we have here. Okay, so first thing first, we want to reshape this log spectrogram. Now, why do we want to do that? Well, we do want to do that because if you remember, for training our variational autoencoder, we needed to add an extra dimension to our two-dimensional spectrogram, a third dimension which is representing the number of channels, right? And so we want just like to strip that third dimension and go back to a two-dimensional array. Now, given this is a NumPy spectrogram, we can use NumPy syntax. And so we'll take this spectrogram here, and then we'll do this. Oops, this and this. So basically what we're doing here is copying the first dimension, copying all of the second dimension, and then dropping the third dimension. Okay, now we have the log spectrogram with the right shape, bidimensional, so 2 dimensions. Okay, so now we want to apply denormalization, and for that we need to call our min-max normalizer. And so here we'll call this denorm log spec, and this is equal to self.minmax normalizer.denormalize, and here we should pass a couple of arguments. So we need to pass the log spectrogram first and the min-max value. So let's jump into this one here, and you'll see like the method definition. And here we have like the normalized array, the original min, and the original maximum here. Well, so we shouldn't pass only the min-max value, because this is a dictionary that has 2 keys, min and max. So here we'll just pass min, and yeah, let's just, oops, copy all of this, and here we'll pass max. Good. Now we need to take our log spectrogram and linearize it. In other words, we want to pass from decibels back to normal amplitude. How can we do that? Well, we can use Librosa for that. So let me import Librosa. So we'll do import Librosa. Now back here, we'll do spec is equal to Librosa dot decibels to amplitude, and we'll pass the what's the name of this guy? Denormalized log spectrogram. Okay, we'll pass that. Next, we'll apply the inverse short-time Fourier transform to get back the signal. So we'll have signal, and then Librosa.istft, and pass two things: the spectrogram and the hop length. So we'll specify it through our public hop length variable. Cool. Now we have the signal. We need to append it to the signals list. So we'll do a signals.append, and we'll pass in the signal. Okay, so by now, at the end of this loop, we'll have all the signals appended to the signals list, and so we can return them like that. Cool. So the sound generator class is now ready, and we should move on to the generate.py script. I'm in the generate.py script, and as you can see, I already wrote a little bit of code. These are like very simple things that I didn't want to waste time on. As you can see, we have a few constants, and yeah, I'll explain them like while we implement this script. And then we have a couple of utility functions. So the first one, select spectrograms, it's quite straightforward. What it does, it just samples a number of spectrograms out of the train set that we have, and then it returns both the spectrograms themselves as well as the relative min-max values. Cool. Then we have this other utility function called save signals. Well, this is self-explanatory, right? So we have like an audio signal and we want to save it to disk. Let's take a look at the core steps that we want to implement for this script. So first of all, we need to initialize a sound generator object. Then we need to load both the spectrograms and the min-max values. So we already saw the spectrograms, but the min-max values are like the ones like stored in this pickle file here. Cool. Then out of these spectrograms, we want to sample a few of them. We'll sample 5 spectrograms, and we'll also sample the relative min-max values. And then we are going to generate audio for the sampled spectrograms. In other words, we're going to reconstruct the audio passing through the whole variational autoencoder, and that's the key of like what we've built like so far. In the next step, we'll directly convert the sampled spectrograms to audio without going through the variational autoencoder. And if you're wondering why we're doing this, this is just for comparison reasons, so that we'll have the fully reconstructed signal going through the whole variational autoencoder, as well as the reconstructed signal, but only starting from the original spectrograms and going back to the relative audio signal using the Griffin-Lim algorithm. And then in the end, we want to save both types of signals. So the ones that we got from the full reconstruction through the variational autoencoder, as well as like the direct spectrogram conversion to audio. Okay, so let's get started with the initialization of the sound generator. So here, of course, we need to import a couple of things. So first, we need to import the sound generator. So we'll do from sound generator import sound generator, but then we also need to import the VAE class. So we'll do from, I think it's called autoencoder, import, VAE, yes. And you'll see why this is needed in a second. So the first thing that we want to do is loading the variational autoencoder model. And we have a class method for the VAE class that is called load. And we should pass here just the save folder where we saved the model that we trained in the previous video. And that is just model, as you can see here. Right. Okay, so now we have the VAE And the next step is that of creating a sound generator. And for that, we need to invoke SoundGenerator, the constructor, passing in the Variational Autoencoder, as well as the hop length. Well, let's just pass it like this, hop length, and this is one of the constants that we defined up here already. Cool, so now we have the SoundGenerator. What next? Well, we need to load the spectrograms as well as the min-max values. Let's start with the min-max values because it's just quicker. As I said, the min-max values are here. This is a pickle file that we got when we went through like the pre-processing steps. And to load this, we need pickle. So we'll import pickle. And down here we'll do with open, and we should pass the file path. And the file path there we could take from here, min-max values path. So oops, we'll take this and we'll open in a reading binary mode as file, and we'll do min-max values are equal to pickle dot load, and we'll pass the file. Okay, we already have a facility that loads spectrograms for us, and we used it in the train.py, so when we actually trained the model. And as you can see here, we have this load fsdd. Now the thing is that this load fsdd only returns the spectrograms themselves, right? But we not only need the spectrograms, but also the relative file paths. And why do we need them? Well, because when we do the select spectrograms, when we'll sample the spectrograms, then we also need the relative file paths. So what we can do is just like take this load fsdd here, and we'll just redefine it up here. So instead of only returning xtrain, we'll also return the file paths. So this is a list with all the file paths associated to the relative spectrum that we return. And so here we have the file path. So here we're going through each of the files, and this is the right time to do a file paths.append, and we'll append the file path. So at the end of this, we can return not just xtrain, but also the file paths like this. Okay, this looks good. Now we can go down here and do a sampled specs. Nope, this is just like the spectrograms and the relative file paths. And we'll do load fsdd, and we should pass the spectrograms path. Now I already have the spectrograms path defined here in train.py, so I'm just going to import it. So I'll do a from train import spectrograms path like that. Cool. So oops. Oh, what happened there? So I'll add spectrograms path to load fsdd, and now we should have both the spectrograms and the file paths served. Cool. It's now time to sample out of all of the train set, basically, a few spectrograms and get also back the associated min-max values. For that, we'll be using the select spectrograms utility function that we have here. So let's do sampled specs and sampled min-max values. So we'll have select spectrograms, and here we should pass first the spectrograms, and this is specs, then the file paths, then the min-max values, and finally specify the number of spectrograms that we want to sample. And I'd say let's go with 5 here. Okay, so now we have all we need for generating these signals starting from the sampled spectrograms. Okay, so let's generate audio for the sample spectrograms. So how can we do that? Well, first, let's create a variable called signals, where we'll store all of the generated signals. And then we'll take the sound generator and we'll call generate. And here we should pass both the the sampled specs as well as the sampled min-max values. Yeah, and we should get back the signals. Now, let's write this other variable here called original signals. And what I mean by original signals is that we are using the spectrograms and we are directly converting them, the sampled spectrograms, we are converting them to audio without going through the variational autoencoder. How can we do that? Well, that's quite straightforward. We do SoundGenerator dot convert spectrograms to audio, and here we pass once again the sampled spectrograms as well as the sampled min-max values. We should save both of them. So how do we do that? Well, we have a nice utility function here called save signals. So we'll call save signals up here, and we should pass the signals as well as the save directory. And the save directory for the generated signals will be save dir generated. So we'll create a new directory called samples and then a subdirectory called generated, and we'll store all of the new signals there. Okay, let's pass this one in, and then we'll do the same thing, but not with the signals, rather with the original signals. And here, instead of passing save dir generated, we'll pass save dir original. This should be okay by now. So if we don't have any errors, it should work. So let's see. Let's run it and see what happens. In the meantime, I'll just close this one here. Okay, so we got an error. I investigated the error and found out that there are actually 3 different errors, but the one that caused that error message is not really related with the code that we wrote today. It is related with the code that I wrote a couple of videos ago when we built the audio pre-processing pipeline. So let's jump in there, take a look at the issue, and then fix it. So in a nutshell, the problem is that when we actually go through the pre-processing pipeline and we pre-process all of the data and we try to store the min-max values, so here in this pickle file, we get basically a dictionary with only a key that's none. That is quite ridiculous, isn't it, right? And I found out why that was. Well, the problem is here. So here we are in a process file. So in this private method, what we do is we pre-process a single file, and when we save a feature, we get back and the feature in this case is the spectrogram, the log spectrogram. We should get back the save path, and then we pass this save path to this other method here that's responsible for storing the min-max value. The problem is that we never return the actual save path, or in other words, the file path where we save the spectrogram. And why is that the case? Well, that's because this save feature method here doesn't have a return. Okay, so now if we do actually add a return here, we should solve all of this initial issue, because now we are returning a save path, and back here we pass that save path in here, and then store min-max value is going to be able to create this new key value index in min-max values dictionaries that then is going to be stored in the file that we saw earlier, this one here. Okay, so this should do the trick. Now, what's a great takeaway lesson from this? And the takeaway lesson is that you always want to have unit tests. If you need to trust your code, you need to have unit tests. Okay, so So now that we fixed this, the next thing that we should do is just running pre-processing this script once again. So you should do that as well if you followed along with the series. Okay, so I'll just like leave it at that for now. And in the meantime, I'll just move on to the next error. So the next error is quite simple. So here we declare these two constants, right? And basically these are like the path to the directory where we want to save the original signal and the generated signal, but we don't create them programmatically, but we have them here, like in the file system. So we need to add them here in the file system. So I'll add samples here, and then I should add both original and generated as two subdirectories. Okay, so let's do new directory, and this is original, and the next one is called generated. Okay, so this should fix this. Now let me just check if the script finished. Yes, it finished successfully, so that's fine. Now there's just one final thing that we should solve here, and it's this one. So now SoundGenerator.generate, so the generate method returns a couple of things. It returns the signals, that's correct, but it also returns the latent representations associated to the spectrograms. So if we see here, you have signals and you have latent representations, which basically means we should put an underscore like this because we're not doing anything with the latent representation. And so, yeah, we'll just assign the latent representations to an underscore variable. And here we have the signals variable. Okay, so with all of these fixes, hopefully we should have our generate.py script working just fine. So let's try that out. Fingers crossed, everything is going to work. So now we're loading TensorFlow. This is working, and yes, it seems it worked correctly. So let's just check if we have audio files in samples and generated. And so we have samples generated, and yes, we have 5 audio files that are connected with the 5 spectrograms that we sampled, and then we should have the same thing here with original as well. So the next step and final step in the series is just to listen to these results. Here we are in the file system. Let's check out the generated samples as well as the original ones. Let's start with the original. So sample number 0.
9.
Okay.
9.
Sounds quite weird, isn't it? Yeah, it sounds very robotic, and the reason is because we are reconstructing the spectrogram, the magnitude spectrogram, using the Griffin-Lim algorithm, and the phase is not perfect, and you can hear these artifacts. Okay, so now let's compare this
9
against the generated version.
9.
Okay, so you've heard that. It kind of like resembles a 9, which is great, and it sounds very similar. That's cool. Now let's move on to another one. Say this.
3. 3.
Okay, this is very, very quiet.
3.
But it's clear to 3. Okay, that's super quiet. So now let's try to open this in Audacity and okay, I'll accept that and amplify this. Okay. Okay, you have the 3 there. That's cool. Okay, let's just try another one.
7. 7.
That's a 7, right? Let's go to the generated version of it.
7. 7.
Okay, once again, it's very quiet, but it's there. It's a 7, and it's quite similar. So let's open it with Audacity another time. Okay, let's call the amplify effect on it. Oops.
7. 7.
7, it's there. That's cool. Okay, so it seems that the sound generator is actually working, which is great news. And so This is it really for this series. I hope you've enjoyed it. By now you should have a very good understanding of autoencoders, variational autoencoders, both the theory and the implementation, and know how to generate data, both image data as well as sound data using spectrograms and all of the trickeries that we've used. So if you enjoyed this series, just leave a like to this video, and please let me know what you'd like to learn next. So leave a comment with your suggestions. That's all for today. See you next time.